Okay, so now we have this f lambda. So yeah, so therefore we know that lambda here is equal to v over f, right? So therefore f dash equals v plus v naught over v multiplied with f. Okay, therefore f dash equals 1 plus v naught over v f. So again, when the observer is moving towards the source, we can assume that we can pretty much identify that the frequency is going to increase because the wavelengths are going to get cramped. Okay, and when the observer is moving away from the source, we know that the frequency will decrease. Okay, this will happen when the observed speed is v minus v naught. Okay, so these are the two formulae. Also, we should know that the difference in frequency, if you want to calculate the difference in frequency, it will simply be f dash minus f. Okay, and in this case, we should know that the f dash minus f would be v naught over v f. Okay, this is the difference in frequency. So the way, okay, in this situation is when observer is moving towards source. This situation is when observer is moving away from the source. So the way that students should approach this is, first they need to identify whether the source is moving or the observer is moving. Then they need to identify whether the source is moving towards or away from the observer, or the observer moving towards or away. So which formula they need to use, they should pick out and then apply that in solving the problem. Okay. Now when we are talking about light, for light, the speed of the source, right, is way less than the speed of light. So in that situation, when we talk about the difference in frequencies, we have f dash delta f. Okay, difference in frequency equals f dash minus f, which is equal to f c over c minus vs minus f. Okay, and if you work this out and taking into account the fact that c is way larger than vs, we will have this to be approximately equal to vs over v or vs over c. Source of velocity of the source divided by the speed of light multiplied by the original frequency. Okay, so this is in the case of light. Okay, this is very well explained on page 9. Again, if the source was moving away from the observer, we would have delta f equals minus vs over c f. Okay, now for light it does not matter because the speed of the source or the observer is way less than the speed of light. It does not matter if the source is moving or the observer is moving. Okay, as long as they're moving apart from each other, you will use this because the observed frequency would have reduced. If they're moving towards each other, we will use this. Okay, vs over c times f. Okay. So 11.2.4 is solving a few problems involving these concepts. 11.2.6 is the formulation of, or rather the discussion of a Doppler radar. Okay, so a Doppler radar basically sends out electromagnetic waves, usually microwaves, and it reflects off a moving object and is received again by the Doppler radar. And by doing so, the Doppler radar can actually detect the speed of the moving object. Now, how does it do that? We know that for electromagnetic waves, which we just talked about, the delta f, okay, equals v over c times f, right? Delta f is the observed frequency minus the original frequency. Okay, so if we have a radar here, okay, and we have an object, okay, so first the radar is going to send out a pulse at f, okay, and the object which is moving here will observe it at f dash. Now this object will reflect the frequency at f dash, and it will be observed here at f double dash. Okay, so we have to basically apply this formula twice. You can see the derivation on page 10, and ignoring a term of v square over c square, because the speed of this moving object is going to be way less than the speed of light, which is the speed at which the electromagnetic waves are traveling. Okay, so we should get the difference in frequency, which is the difference in the observed frequency f double dash, okay, minus the original frequency f which was sent out. Okay, so received frequency minus transmitted frequency is given by 2v over c f. Okay, where f is the original transmitted frequency. So we know the speed of light and the transmitted frequency. We can calculate the speed of the moving object by knowing the difference in frequency. So we have the original frequency, we have the received frequency, and we know this, so we can calculate p. Okay, so that's pretty much the end of Doppler effect. There's one important point towards the end. If you look at example 1 on page 11, it talks about how the Doppler effect can be used to study the to estimate the speed of blood flow in arteries. Okay, so there have been exam questions like multiple choice questions to identify which phenomena can be used to find the speed of blood flow in arteries. So the student should know that Doppler effect is the phenomenon that can be used. Okay. All right, and also this observation here, they should be well versed with it, because it does not appear on the formula booklet. So they should know when to use this and in what situations they can use this kind of this formula. Okay, so that is Doppler effect, and now we move on to diffraction. Okay, 11.3 is diffraction. Now, diffraction, as we had discussed in the SL portion, happens due to the Huygens principle, and every wave point on a wavefront acts as a secondary source of circular wavelets. Okay, so we saw that when a wave passes through an aperture or a slit, which the wave will assume a diffractive pattern. Okay, now when this aperture is approximately the same order as the wavelength of the wave, we have something called a diffraction pattern. Now on page 11 you can obviously understand what a diffraction pattern is. We have a maximum fringe, a fringe of maximum intensity in the center. That's obviously because of a constructive interference pattern, and we have minimas and then small peaks after that as well. So we'll only be concerned with the central fringe and the first minimas. So the minimas will happen because of destructive interference. Now, this kind of a pattern, it's important to remember the criteria is that B over here, which is the slit width, okay, this has been expanded for explanatory purposes, but B should be of the order of the wavelength of whatever wave we are talking about. Okay, so so now how do we get the first minima? Let's assume each point throughout the slit as a secondary source of a wave, right? So the path difference between A and let's see, let's call this point P over here. The path difference between AP and XP, okay, is going to be this distance over here. Okay. Now, in order for destructive interference of AP and XP, this distance should be half a lambda. Okay. Now, if those 2 points destructively interfere, okay, and the path difference is lambda by 2, then the path difference between the next point and the next point here is also lambda by 2. Then so on and so forth. We had the path difference of lambda by 2, lambda by 2, and lambda by 2. So each point, which is half a lambda apart phase difference wise, will destructively interfere with the other point, and therefore we have half of the slit over here destructively interfering with the other half, and therefore we have a minima over here. Now when we do that, and this is lambda over 2 from similar triangles we can see that by over here must be lambda, okay, twice of lambda by 2. So in this triangle ABY we can see that sine theta equals lambda over b. B is the slip width. So now sine theta 1. Now for small angles, we are only talking about very small angles in radian of angular separation. So theta 1 and theta 2 are both very small, and so let's approximate theta 1 and theta 2 to theta. Okay. So therefore we have sine theta equals lambda over b. Now for small theta, okay, we have sine theta to be approximately equal to theta. So therefore what we have is theta equals lambda over b. Okay. Now this here is the basic defining formula for this is the angular separation for the first minima in a diffraction pattern. Okay. Now we can also calculate this difference over here. So from this calculation over here, we know that theta also equals d over f. Why? How do we get that? Because in this triangle, p, x, and let's say d. Okay, p, x, d. In this triangle, tan theta 2. Okay, tan theta 2 is equal to d over f. Okay, and for small angles, okay, we have tan theta approximately equal to theta. So therefore, theta equals d over f. Because for small angles we have approximated theta 1 and theta 2 to theta. So when we have that theta equals d over f, we also have theta equals lambda over b. So we can get this result, lambda over b equals d over f. Therefore, d, which is the separation from the center of the maxima to the first minima, will be equal to f lambda over b. Okay, so this d is half the width of the central maxima. Okay, and this theta is the angular separation till the first minima. Okay. Now this case is when we are considering rectangular slits. Okay, when we are talking about circular slits or circular apertures, for example the eyes, we have to add in a factor of 1.22 to this formula. So then in that case theta will be equal to 1.22 lambda over b. Okay, for circular apertures. So that covers diffraction. Now we'll move on to resolution.